Good evening and welcome to all the Sigma members and also members of our affiliated and sister clubs to the Sigma meeting for May 2021. For those of you who don't know me, my name's Pete Sherman. I'm the chairman of Sigma and I'll be your MC for the evening. Helping me in the background, we have Richard Oakley and Mick O'Donnell. They're the Zoom co-hosts, and they'll be keeping an eye on everything technical. You shouldn't see much of them, not unless something goes terribly wrong with me, if I drop out something like that. Also tonight we have Stuart Brooks with us, who's going to be doing the space news in the second half. But just before I start with the meeting, you will have probably read in the newsletter that one of the Sigma members, Dave Williamson, had a nasty mountain bike accident last month. I wasn't going to mention just how bad, but I will tell you, he suffered 7 broken ribs, a broken collarbone, and if that wasn't enough, he had a punctured lung as well. He did spend time in Aberdeen Royal Infirmary, but he is back home now with Donna. I'm not sure if they're with us tonight, because Donna's now obviously looking after Dave, so she's feeling quite tired as well. So, but I think you'll like to join with me and wish him a speedy recovery. Okay. Anyway, tonight we will be looking at the sun with a microscope with Lyndsay Fletcher. This title has intrigued me ever since we went on to the program. It's intrigued me very much, and I'm sure it's doing just the same for yourselves. I'll just do a quick run over the Zoom controls for you, just because I know we've got 1 or 2 possibly new members here tonight. So what we're going to ask you to do, if you've got any questions, please put them into the Q&A. You can do this at any time throughout the presentations. You don't have to wait until the end. Just open the Q&A box, put the question in there, and Richard will keep an eye on the questions, and he will then ask them to Lyndsay at the end of her talk. Also in the toolbar, you will see, there's a chat button. I can see quite a few chats going on already. If you want to chat to everybody in the room, just make sure you change the setting from all panelists to all panelists and attendees. That way you'll be able to talk to everybody in the room. If it's on all panelists, it'll just come through to me, Mick and Rich. Okay, so say the Q&A, any questions, put them in the Q&A, don't put them in the chat, because they'll get lost in that chat there and we probably won't get asked to Lyndsay. You'll also notice we've got closed captions working. Now, if you don't want those on, you can turn them off nice and easily. You'll see where it says live transcript and it's got CC above it. If you click the up arrow on there, you can just click hide transcript and that will get rid of them for you. Or if you do want them on, you can move that box anywhere around the screen if you want to as well, depending on your operating system. I'll just put that in there. Okay, once again, we'll be having the members gathering after this meeting tonight. The link for that will go up in the chat box at the end of this meeting. Please do come along. I think Lyndsay and Hugh is going to be coming over as well. So if you've got any questions that didn't get asked or think about afterwards, you can have a chat with them one-to-one. It's a great way for us to keep together and just keep the social side of the club going, which is a great part of Sigma, as you all know. Okay, the meeting brief. Tonight we'll be having a talk, as I say, by Lyndsay. Richard will be handling the Q&As, and we'll still have our little 10-minute break so you can get yourself a cup of tea. I know it's not the same as going and get one from Dave and Donna when they were doing the teas in the hall. After the break, Richard's going to do the members' photos. Stuart Brooks will be doing space news, and then I'll finish off with a little bit of club news. We look at finishing around about 9:30. Might be a little bit earlier as we've got no space news tonight because the sky is just too light for space news, any sky at night, because the sky is just too light. So on to tonight's main feature. It gives me great pleasure to welcome back to Sigma Lyndsay Fletcher. I would like to think of Lyndsay as a great friend of Sigma now. She's done many talks for us for over many years. The last time was in November 2015 when we sounded out the sun and stars. I still can't quite believe it's that long ago. Lyndsay is a professor of astrophysics at the University of Glasgow who specializes in solar flares. In 1993, she joined Utrecht University as a postgraduate researcher. She was appointed a research fellow at the European Space Agency in Nordwijk, and I'm going to apologize for all these names. I'm going to get them all wrong. I know I am, but I'm sure Lyndsay will put me right. If not Lyndsay, Martin de Veer will, because he's here tonight. Those places were in the Netherlands in 1996, where she remained for 2 years working on the Solar Hemispheric Observatory. That's Soho, if I remember rightly. In 1989, she joined Lockheed Martin at Palo Alto in California, using the Yoko and Trace satellites to study flares and plasma jets from the sun. She returned to Glasgow in 2000, becoming a lecturer later that year and a professor in 2014. 2015, she was appointed president of the International Astronomical Union Commission E2 on solar activity. Commission E2 on solar activity represents members that study a wide range of dynamic phenomena produced by our sun. Between 2014 and 2016, she led the seventh framework project, FP7, Project F Chroma, which included a citizen space project, F Hunters. She co-edited a book, Solar and Stellar Flares, in 2017. Now, this book must still be fairly popular, I think, by looking at the price of it. Looked yesterday and it was £68, and that's half price at the moment. So maybe that's one for your maybe that's one for your sort of Christmas list later on. Okay. She was elected a Fellow of the Royal Society of Edinburgh in 2014. She served on the science working group for the Daniel K. Inouye Solar Telescope. She is an advisor for the Roslin Centre for Solar Physics at the University of Oslo, and for the, I'm not going to try and say that one. When did I print that one out? Keppenherg Institute of Solar Physics.
Keppenherg.
Close. Neither there. So as you can see, she's quite a busy lady. But I'm so glad you've given up a little bit of your time for us, Lyndsay, to join us tonight. And everyone, would you please give a socially distanced welcome to Lyndsay Fletcher again? Over to you, Lyndsay.
Okay, thank you. It's a pleasure to be here. I just wish I could be up there in the Northeast. I love it up there, but well, we take what opportunities we can right now. So let me share my screen, and you can tell me if it all looks all right.
Yep, all looks good, Lyndsay, and we can hear you, so it's over to you.
Right. So, solar microscopes. An intriguing title, you said, Pete. I hope that this doesn't disappoint. What I'm intending to really do today is talk about the technology that we use to look with very high magnification at the sun. That's the reason for using the words microscope. I mean, basically it is just telescopes, but we're talking about very high magnification devices. And this beauty here on the left is the Daniel K. Inouye Solar Telescope, which I'm going to concentrate on in the second part of the talk, sort of the later part of the talk. And this is going to be our workhorse in solar physics for the next couple of decades to come. Now, in the past, I've tended to come and talk to you about telescopes in space, telescopes which are observing in X-rays or ultraviolet or extreme ultraviolet wavelengths, where we need to be above the atmosphere. But that's not what I'm talking about today, because we're talking about high magnification. And for that, we just need big mirrors. We need big mirrors or big lenses, and that's just too expensive for space. You can't, well, okay, if you're a rich community of astronomers that can afford to put the James Webb Telescope, which is, how big is its mirror? I forget. But you've got enough momentum behind you to get a lot of money to put a big complicated thing like the James Webb Space Telescope in space, then fine. But solar physics is a fairly small community, and generally we can't get the money or the backing to do that. And so if we want to do high magnification science, we have to do it from the ground. This picture here shows you as I've plotted, depending on wavelength of the radiation, it shows you the transmission of the Earth's atmosphere. And so here's 0%. So where it's brown here, basically none of the radiation gets through. So we have to put, telescopes up in space to see X-rays and extreme ultraviolet and so on in here. From the ground, there is high transmission. So this goes all the way down, and you can put telescopes on the ground and see the radiation. And then there's gaps here and there in the spectrum going between, so the units are a bit funny, but here a few hundred nanometers is a few thousand angstroms, which is the visible part of the spectrum in here. Then we've got some infrared and some terahertz, and then we've got a great big gap here, which is radio. And one day I'll come and talk to you about solar radio astronomy. But what I'm going to be talking about is what most amateur astronomers would recognise as a telescope, a great big collecting dish or a mirror or lens on the ground looking at the sun in the optical, primarily the optical, or maybe the so-called near infrared part of the spectrum. So that's what I'm going to be talking about. And we do it from the ground because it's too expensive to do it in space, but it also means that you can instrument up the telescope. You can put lots of different detectors and cameras on there, which again, you can't do in space. It's too expensive. So we're looking at the optical part of the spectrum. Let's just remind ourselves on the sun, the bits of the sun that we're talking about. When we're talking about the optical part of the spectrum. Well, first of all, we're talking about the photosphere. The photosphere is a temperature of about 5,500 degrees centigrade. And we just talk about that as being white light or continuum. And it's telling us just about the hot, visible surface of the sun. That's what we see with our naked eye. And then the other parts of the sun's atmosphere, actually I've just realized I've forgotten a very important third part of the sun's atmosphere. I'll come on to that later though. The other important part of the sun's atmosphere, which we can see in the optical, is its chromosphere. Chromos is Greek for colour, and it reflects the fact, particularly when you see during a solar eclipse, you see these sort of bright red structures, which are called prominences. The chromosphere is typically a temperature of about 10,000 Kelvin. It's a few thousand kilometres thick. The radius of the sun, just to give you kind of scale, the radius of the sun, so the distance from the centre to the edge here, is about 700,000 kilometres. And so the chromosphere is a few thousand kilometres thick. It's just a thin skin of the surface of the sun. And what we're seeing here is the H-alpha line of hydrogen. Hydrogen is the most abundant element in the sun, in the universe in fact, but certainly in the sun. And the H-alpha line is a very strong transition, very strong spectral line. And those of you who are fortunate enough to have a Coronado or a Lyndsay Solar Telescope will be used to observing in this spectral line. It looks absolutely stunning when you see it with your own eye. Okay, so that's typically the kind of things that we can look at with the visible part of the spectrum from the ground. Of course, the third bit, which I haven't done here, is the corona, and that's visible during a solar eclipse. And one of the telescopes I will talk about will be able to observe the corona, but it's not typically done because it's really rather hard to do unless you have an eclipse. Okay, so there's another view of the sun in three very popular observing bands for professional and for amateur astronomers: white light or continuum, calcium K, and you can get amateur telescopes. I think they're pretty expensive to observe in calcium K, and H-alpha. And this setup down here, I just found this last night. I have to get in touch with these people. This is the Technical University of Darmstadt, and they have this this four telescope arrangement. Everything's kind of clamped together, and it's observing. It has one high resolution camera in the middle, and then it's got these three complementary wavelengths from these three separate cameras around the edge, and they are observing very, very regularly during the summer. They're taking an image every second or so, and so I found this last night for my own work, which is on solar flares. It'll be marvelous. Okay, right, what do we see when we look at the photosphere? Here are the typical features that we might want to study on the photosphere. This image here shows what's called the solar granulation. These sort of irregular cells here, and that is the boiling surface of the sun. Slightly hotter in the middle, and therefore slightly brighter than at the edges where the material is cooling and falling back down. So hot material rises in the center of one of these cells and then cools and falls back down at the edges, and so it looks a bit darker where it's cooler. So that's the granulation, boiling surface of the sun. This stuff here, this very fine stuff here, is called the filigree. And we think that that is places where there's very strong, concentrated, small bundles of magnetic fields. Anybody who's heard me speak before will know that when we talk about the sun, we have to think about this strange thing, the magnetic field of the sun, which is responsible for all of its activity and has all these strange effects on the surface of the sun. All these little bright points as well are probably magnetic. Now, just to give you again an idea of scale, from side to side of one of these granulation cells is about 1,000 kilometers. I'm sorry, I'm not going to use miles, I'm going to use kilometers, but what's that? It's about 600 miles, I suppose, from side to side. But again, that's very small in terms of the whole disk of the sun, which has got a radius of 700,000 kilometers, a diameter of 14 million kilometers, 1.4 million kilometers. Okay, and so these are features which are associated with the energy transport in the sun in the case of convection, how the energy gets from the center of the sun to the surface of the sun, and the magnetic field. And then this image over here on the right also shows, I don't know, maybe I can change the color of my laser pointer because you can't really see red very well on that. Let me just try and do that, excuse me. Laser pointer, pen, laser color. Let's try blue. That's maybe better. Okay, blue. So here we can see, of course, sunspots, which are cooler regions of the solar surface. Maybe the temperature here, instead of being 5,500 centigrade, is maybe about 4,000 centigrade in the center. And then we have the in the umbra, and then the penumbra is a little bit warmer than that, somewhere in between. And you can see these are very highly structured. They've got these kind of linear features poking out. And again, this is telling us about the magnetic field, the shape, the direction of the magnetic field. And then this other sort of bright stuff, don't know what else to call it, bright stuff called faculae, means little torches in Latin. And so lots of stuff to look at, and there's good physics questions behind each of these things which we want to understand. I mean, to be honest, we don't understand even how a sunspot forms. What process makes that bit of the sun become darker? And when you watch it form, it doesn't just pop up fully formed, it kind of condenses from lots of smaller little bits of sunspot. And so there's lots of interesting physics questions to do with everything that we see in the photosphere. The chromosphere as well has got lots of bits, lots of stuff. Here's a nice image in H alpha again. And so we can see things like this dark linear structure, this one here, this is a filament, this is cool material. It's cooler than the rest of the chromosphere. Chromosphere, remember, about 10,000 Kelvin, so maybe this is 8 or something, you know, just a little bit cooler, cool enough that it is absorbing the radiation that comes from the chromosphere, and so it looks dark. So, and when one of these things makes it over to the edge of the sun, the limb of the sun, it becomes bright in comparison to the background, and it's called a prominence. Filaments and prominences are just the same thing. And we think that this is cool material which has been levitated into the atmosphere of the sun due to its magnetic field. Very dynamic, lots of flows and brightenings and so on, all kinds of exciting stuff happening here. You can just see a sunspot. There's a sunspot here and there's a sunspot there, you can still just see. And then this brightening inside the sunspot group is called the plage. Lots of nomenclature. And then if we zoom in, we can see this forest of spiky things called spicules. And this is observed in H alpha, but not exactly in the center of the H alpha emission line. This is an off-band observation of 0.7 angstroms to the red. And again, if any of you have used a Coronado and have played it, or a Lund, and have played about with the tuning, the wavelength tuning, you'll recognize that as you tune through the spectral line, you see different things. You see things appearing and disappearing as you go from one side, like the blue wing of the spectral line, through the center and out to the red side. And that's because the offset, this number of whatever it is, 0.7 angstroms in this case, this is related to the speed of the material that you're able to see at that exact wavelength. And so if you tune through the line, you basically see things moving at different speeds in the atmosphere. Spicules are a very big, very hot topic right now in solar physics because they extend up into the atmosphere of the sun. They carry mass, they carry energy. And one of the biggest problems in solar physics is how do you heat the outer atmosphere of the sun, its corona. And it's thought that spicules might be an important part of that by bringing energy up into the corona. So this is a very hot topic. So there's lots and lots of good observational things to focus on and lots of good science questions to address with solar microscopes by zooming in great detail. This, I suppose, this image here is from the Swedish Solar Telescope, which is one of our better solar microscopes right now, but it's soon, unfortunately, going to be made redundant by the next generation coming along. Whereas this is obviously a large, a sort of full disk, part of a full disk, which shows the global context, but doesn't show the detail. So this image from the SST, it leads me in quite nicely to, I'm just going to show you some nice big telescopes. I don't often get the chance to do this, but I love big telescopes. I wish I'd been an engineer, in fact, and involved in designing these things. But here is one of the big telescopes that we have just now. Now, in a few slides down, I'll just say a little bit more about not exactly magnification, but about what's called angular resolving power of a telescope and how it's related to the size of the telescope, in particular the size of its main collecting element. And that main collecting element can be a mirror or it can be a lens. The Swedish Solar Telescope up here in La Palma is a very unusual telescope because it's the biggest telescope with a lens here. It's and you can see the lens, you can see the sun through the lens. This is the lens here. Now, it's not pointing at the sun right now. Imagine that was being, it was turned over for a publicity shot. But the lens is at the front of the telescope, and the entire tube, so here it is pointed at the sky, and it's a convoluted design because the telescope has to track the sun across the sky. The sun is not moving at the same rate as the rest of the sky. It's moving at its own rate across the sky. Slightly different from the rest of not very much different, but slightly different from the rest of the sky. And also you want to keep the image rotated so that it's got a fairly constant orientation on your camera. And so you've got to have some complicated rotating optics which do all that correction. So the light comes in here and then it bounces off a mirror there, and then it bounces off a mirror there, and then it goes all the way down this big tube to the detectors at the bottom. And the whole thing is kept under vacuum. Used to be called the Swedish Vacuum Solar Telescope, but they took vacuum out of there at the same time as they increased the diameter of the lens from 0.5 metre to 1 metre. Now think about this, a piece of glass which is 1 metre across. That's a pretty difficult thing to make with high optical quality. It's also a pretty heavy thing and a difficult engineering job to get this lined up and stable. So this is the biggest telescope in the world in terms of its diameter, which has got a lens as its primary optic. And that was responsible for those beautiful specule pictures before. This one is still working. We still get data from it. It's got some really great instruments in it. In fact, I've got a couple of PhD students just now who are analysing data on solar flares from an instrument called CRISP on the Swedish Solar Telescope in La Palma. Okay, another beauty here is the McMath Pierce Solar Telescope. I put this up just because it's such a iconic telescope. It has a 1.6 metre primary element, but this time it's a mirror. I'm not quite so familiar with the optical layout of this, but this is the light path down here. In fact, I think that this is what's called the dispersing arm of a spectrometer, which sits somewhere down the bottom here. And this is at Kitt Peak in Arizona. Lovely, lovely instrument, lovely telescope, nothing wrong with it. But the National Science Foundation decided to stop funding it. And so now it's retired, although it's going to be reinstated as a visitor centre. And one of the reasons for that is because the national park that it's in, one of the conditions of getting the land for this telescope back in the 60s or 50s or wherever it was that when the telescope was decommissioned, they had to remediate the land. And this thing is sitting on a bearing which is full of horrible chemicals. It's probably got mercury and other stuff in there, and the ground is not in a good state. So it's going to be too expensive to remediate it, and so they can't close it down completely. They have to keep it open for something, and so they're going to keep it open as a visitor centre. But it was a great telescope and provided some very unique observations recently, particularly in the far infrared part of the spectrum. That's a bit of a shame that it's no longer with us. And then the third one, which I'll focus on just now, is this. This is the Big Bear Solar Observatory in Big Bear Lake in California. It also has a 1.6 metre mirror. And so you can see the main telescope poking out here. Now the telescope is now called the Goody Solar Telescope, named after Phil Goody, who was the director there for many years, now retired. And it's been a marvelous telescope. Big Bear Lake is a great place for a telescope because being surrounded by water, it avoids a lot of the thermal currents, the heat currents, which disturb the atmosphere and lead to image stability problems, which we'll talk about, the so-called atmospheric seeing. So that's just a few of these, solar microscopes. These telescopes which are observing in very high detail. And as I mentioned before, it's possible with a ground-based telescope to put lots of instruments on, more than you could put up in space, because it's too expensive. And also the good thing about being on the ground is that if something breaks, you can go and fix it, and you can fiddle with it and you can improve it. Whereas once it's in space, that's it. And so these telescopes are constantly getting upgrades and updates, and so they, in some sense, they last a lot longer than the space telescopes. So with a number of instruments, you can do many different things almost simultaneously. So in the background here is one of the images that I'm more used to showing. This is an image of the solar corona seen by the Solar Dynamics Observatory Atmospheric Imaging Assembly. And the Goody Solar Telescope will typically look at a little square about this size. And you can simultaneously look, you can look at the corona with the Solar Dynamics Observatory. You can also look in the chromosphere and at the same place in the photosphere. And this telescope also has a means to measure the magnetic field. And so you can kind of stack up these different wavelengths, these different layers in the atmosphere. This is kind of an order of height, high in the corona, the chromosphere, a few thousand kilometers above the photosphere, and then the magnetic field, which is actually visible at the photospheric level, but using different technologies. And so you can start to get a kind of integrated picture of how everything connects together in the atmosphere of the sun. So that's the Goody Solar Telescope kind of raison d'etre, is to make these connections, but it does so at beautifully high spatial resolution. So here's just an example. Now this is black and white. It's not beautifully coloured like a lot of these images, Basically, these cameras all work in black and white. It's not color cameras on the back, it's just a black and white camera. It's a CCD detector, which detects intensity, not color. And then later on, if you want to make a beautiful image for publicity, then you colorize it. But the native data is just black and white. So this is just taken from a paper which was published a couple of years ago in Nature Astronomy. And it's actually part of a flare, my favorite thing. And you can see here a sunspot and another sunspot there. And there are two regions here called FA and FB. These are flare ribbons A and B. It's just what they've called them. And I hope that you can see how fine the detail is here. There's just extremely delicate structure which is able to be seen in this single still image. Again, here we're looking off band H alpha, so we're looking out in the red wing of H alpha. So when we see something bright, it basically means it's moving, and the red wing means it's redshifted. And so typically what we'd be looking at here is gas, which is emitting in H alpha, but it's moving a little bit, it's moving down. But in fact, more interestingly, let me see if I can play the movie. I had a little movie here. I don't know how well that will play on people's screens, because I know there's bandwidth issues. I don't know whether anyone can say, can you see the movie?
It's fine, Lindsay.
Is it okay?
Yeah, it's fine.
Excellent, right. So this is really lovely. You see these flows here. Again, we see the flows, not this time because the gas is emitting in H alpha, but actually because it's absorbing in H alpha. And so it absorbs the radiation which comes from behind, and so it looks dark. We see that absorption very strongly because we're in the right part of the spectrum, we're in the line wing, and so we're seeing moving, absorbing material. And so here we're seeing, well, what we think has happened is that previously that material had to get up into the atmosphere, being heated by some means, and then it cooled and started to fall back down. This is now sometimes referred to as coronal rain in certain circles, and you can see that there's flows going in two directions. It's going that way, but also going down on the other side as well. Sorry, I'm not in control of my cursor here. So you get this sort of rain of material. So up here somewhere, where those two flows separate, there's a lot of hot material which is cooling and falling back down onto the surface of the sun. And you know, as a flare scientist, I just get so excited when I see these data. You know, when I look at these brightenings which are rushing across the surface of the sun, even rushing into the center of a sunspot. From a point of view of understanding what the magnetic field is doing at that point, it's really rather confusing, but it's gorgeous. I hope you agree, it's an absolutely gorgeous movie, and it is at a level of detail that we just could not do from space. 1.6 meter telescope, we can't do this in space. So the scale on this, if you look at these tick marks, this is in arc seconds. And so, you know, one of these tick marks is 1 arc second. An arc second is a 60th of an arc minute, and an arc minute is a 60th of a degree. On the sun, an arc second is equivalent to a distance actually on the surface of the sun of 720 something kilometers. And so we're getting detail at very much finer spatial scales than that. You know, it looks like the detail there is maybe about 0.1 of an arc second or something. So really very high detail achieved, but let's just think about how this is done, because at first glance it's actually not obvious. So, maths and equation. I hope you don't mind seeing an equation on a Friday night, but this is an easy one. This is a fairly easy one. This is an equation which we teach all our first years. We teach them the background to it for what's called the angular resolution of a telescope. The angular resolution is a way of describing the level of spatial detail that can be detected. You know, I'm saying things like an arc second is 725 kilometers on the surface of the sun. I can say that because I know how far away the sun is, but basically all we measure is angle. All we know about is angle. To turn that into a size, you have to know how far away something is. I'm sure there's a Father Ted joke in there somewhere. But to determine the angular resolution of the telescope, you have to use this equation. Alpha is the angular resolution, and it's 1.22 times the wavelength divided by the diameter of the telescope. So you can see that if you've got a big diameter, a big number here on the bottom of this fraction, of this ratio, then you have a small value of alpha, which means that you have a high level of spatial detail that can be detected. You can detect a very small angle, or you can detect changes on very small angular scales. So the bigger D is, the bigger the diameter of the telescope is, the higher magnification it is. This is the Rayleigh criterion. You can look at it another way. You can look at it in terms of the ratio of the diameter of the, if it's a standard Galilean telescope or something like that. You look at the ratio of the diameter of the eyepiece to the diameter of the primary to the diameter of the eyepiece, and then you get an actual magnification number out, but you can also think about it in terms of the angular resolution. So if we just do the numbers, this is like a first year exam question for first year astronomy. If we do the numbers, here's the wavelength of hydrogen, alpha, in nanometers, 10 to the minus 9 meters, and here's the diameter. Then we get, this is alpha, okay? 5 times 10 to the minus 9 in units of radians, but we turn it into seconds of arc, it's about 0.1 seconds of arc. So that actually sounds about right. That sounds like roughly what we could see in that image before. 0.1 seconds of arc is about the size of a thing that we could see. However, at Big Bear Lake, the seeing, what's called the seeing, is about 10 times bigger. What do I mean by seeing? Now, if you've looked at the sky with a solar telescope or any telescope, you know what I mean by seeing. It's what makes images dance about and wobble and distort and do that annoying stuff. So here's a picture of a jet above hot tarmac, or sitting on hot tarmac, and there are thermal currents, air currents coming off the hot tarmac. It's not so much that it's hot that's the problem, it's that it's lots and lots of pockets of air with slightly different densities. And those slightly different densities distort the rays, the light rays which are coming from the plane to our eyes. And so it all wobbles about, it shimmers, it's not clear. And it's possible to measure what's called this is called seeing, atmospheric seeing, although normally that's when you're looking straight up at up through the atmosphere. It's possible to measure that. There are devices you can use to measure what the seeing is and record how much the image of a star jumps about, for example. And at Big Bear Lake, the seeing is about 1 arc second, which means that you shouldn't be able to see this level of detail. It should be all smeared out so that this finest thing you can see is an arc second. So there's something else going on here. And that is the magic of adaptive optics. So here is a picture of a star. This is a star seen through the turbulent atmosphere. Now, a star should essentially be a point source, but it's not. It's jumping about. It doesn't look like anything circular or anything like circular. It's jumping. This is taken at a rate of about, I think this was about 50 frames per second. Maybe it was even faster. And you can see the things jumping about. And it's very distorted. It's not like a point source at all. However, it can be corrected using what's called adaptive optics. Now, I should be able to run that again, so you can see the difference of adaptive optics. Let me just do that again. Okay, so that's the same observation, but with a technology called adaptive optics switched on. It's the only reason we build big telescopes. If we didn't have adaptive optics, we would be reliant on capturing the sky through particularly steady and stable periods in the atmosphere's behavior. doing lucky imaging, for example. When you've got a telescope which costs hundreds of millions of dollars, you can't take that risk. You've got to get all of the good observations that you can. And so adaptive optics is a technology which has been developed over the last few decades, has really come into its own when we now have big computers basically to do the necessary calculations for us, and is being used on all of these big solar telescopes now. This is why it works. So I'm going to try and give a kind of sketch of how adaptive optics works. I think it's a magical technology. Rather complicated, but magical. So here, let's think, this is the light which is coming in from the main mirror of the telescope, and it's distorted, called here a distorted wavefront. We saw the effect of the distorted wavefront on the image of the star, the image of that plane. Everything's kind of wobbling about. Now, what we need is a bendy mirror. This is called the deformable mirror or the adaptive mirror. And this bendy mirror is made up of lots and lots of segments. You can see an example of a small adaptive mirror here, or deformable mirror here. Lots and lots of different segments, each of which can be independently controlled. And here you can see the wires that go in to control little pistons on the back of each called actuators. And so this mirror is wobbled thousands of times a second. Each bit is wobbled thousands of times a second to basically take out the distortion in the wavefront. So this bit of the wavefront here, you know, it hits that part of the adaptive mirror, which changes just a little bit, so that when the wavefront is reflected off the mirror, it's not wobbled anymore. It's not corrugated, is the name we use. It's nice and flat, and the image is very stable then. And so that's basically, that's one of the essential components. The light coming from the adaptive mirror is then, well, most of it with its corrected wavefront goes through, you know, a lens and then into a camera, but some of it is split off. This is a device called a beam splitter, which is just a partially silvered mirror. Normally it lets sunlight through and sends sunlight in another direction. And here is another essential component of adaptive optics. It's called the wavefront sensor, which is a technology which allows you to work out exactly how corrugated that wavefront is, exactly what the shape of the wavefront is. And it's not as complicated as you might think. You actually just do it with a lot of little lenses together. We can talk about that later if people want to know. But anyway, this device works out the shape of the wavefront, works out how much you have to correct the wavefront by, calculates what force you have to put on the piston on the adaptive mirror, and sends it through a computer control system up to the mirror again. And so when you've got this working, there's a very nice feedback between the adaptive mirror and the wavefront sensor. It's all going at thousands of calculations per second, or rather the calculations are probably faster. It's going at thousands of actuations per second. And eventually what comes out is a stable image with the effects of the atmospheric seeing not completely removed, but mostly removed. And so here's just an example. Actually, there's a little bit more that we can say about this. So here's an example of what happens. The outside of this image here of the solar granulation, you can see it looks kind of fuzzy and rubbish. You know, if you just spent $200 million on a telescope and you got that out, you'd be very happy. This bit in the middle has had adaptive optics corrections applied. Similarly here in the middle of the sunspot, the adaptive optics corrections have been applied, but on the outside, they can't be applied. And that's actually because, you know, it's not a panacea, adaptive optics. It's only got one, classical adaptive optics has got one deformable mirror and can correct only over a very small field of view. And this is tiny. This is a really tiny patch. It's far smaller than a sunspot, so you would never get a whole view. But there's actually other developments in this as well. People are doing what's called multi-conjugate adaptive optics, where you don't have one, but several deformable mirrors. And this is a result with 3 deformable mirrors. And you can see that the correction's good over a much larger field of view. So this is a technology which lets us still the atmosphere something which, before we had computers, before we had electronic devices to capture the radiation, there was no hope of doing this. But now we can still the atmosphere. Here is, I think this is a movie as well. No, it's just a picture. Classical adaptive optics. Again, it just shows you this small patch in the middle, which can be corrected. But then this is switching between MCAO, multi-conjugate adaptive optics, and classical adaptive optics. So there's MCAO switched on, and you can see that there's a much clearer view over the whole field of view. This is, of course, this is also a Big Bear Solar Observatory. So back to classical, fuzzy on the outside, clear in the middle. MCAO, it's clear over the whole field of view. Very nice data over the whole field of view. So this is the other technology which allows our solar microscopes to work. big mirrors, great big mirrors, and adaptive optics. Okay, right now I'm going to just talk a bit about the DKIST, the Daniel K. Inouye Solar Telescope. So I've been on the science working group for this telescope basically since it came to, well, basically since 2006, when they really started planning and seriously. So the science working group is a team of scientists that basically says, okay, what are the problems in solar physics that we need answers to, and how can we design a telescope and detectors, instruments to address those problems? That's our job in the science working group. So I've had a long and happy relationship with this telescope, the Daniel K. Inouye Solar Telescope. It's our biggest solar telescope. It is located on the beautiful holiday island of Maui, up here on the top in the Haleakala extinct volcano. And so you can see, this is a picture of it. You can see this is all volcanic rock, and it's above the clouds. And there's the sun up there in the background. This is you might know that telescopes in Hawaii are having a bit of a rough ride right now. There's a lot of native Hawaiian groups that are very protective, rightly so, of their holy places, their religious places, their special sacred places, which are volcanoes, which is where, you know, we scientists and engineers want to put telescopes. And so it's a difficult cultural problem. There's strong pros and there's strong cons. You know, I always think, well, what if somebody wanted to put some big ugly thing on top of Ben Nevis? I wouldn't be very happy about that. And for the native Hawaiians, it's even more upsetting, because it's not just about how it looks, it's about what it means. It's about desecrating their landscape, desecrating their religious places. So this has been built. It's probably the last telescope to be built on any of these islands, though, to be honest, because there's such a fuss about the next thing that was planned, which was the 30-metre telescope. I would be very surprised if that ever gets built, to be quite honest, on that location. They're already scouting in other places for a location for the 30-metre astronomical telescope. Yes, so however, DKIST got in under the wire, and here it is. This is its enclosure. It's a 4-metre mirror, and so that's going to do great things. The magnification is going to be extraordinary for this. It's kind of a space age looking thing. You can see all these things around the side. These are louvers. They let air in because you have to get a very good steady airflow through the dome to try and keep what's called dome seeing down. This, remember, it's not like a telescope running at night where it's nice and cold and the air is kind of stable and cool inside the dome. The air is hot inside the dome, so you have to try and cool it and keep it flowing in an even way to get rid of the so-called dome seeing, not atmosphere seeing, but dome seeing. This is the main aperture where the light comes in, a great big hole, and inside is the telescope. Now, most astronomers can frequently show pictures of their trip to the telescope. My telescopes have previously been in space, and so I can't, but now I can. Hey, I've been at this telescope. I know my eyes fill with tears when I think about these trips, because it was very emotional to see this thing being, you know, come to fruition after many, many years. In fact, it only got built because of the what was it called? You know, after the crash, Obama. In 2009, Obama piled a lot of money into public works projects, and the NSF got money for this telescope. They got the $300 odd million needed to make it a reality. So there's me with a few other members of the science working group outside the telescope, and here is inside the telescope, and this is the primary mirror here. This is the only time in my life I've ever had to wear a hard hat and a high-vis jacket. And so here's the primary mirror, and you can see some electronics at the back, which we'll talk about a little bit as well. Inside the dome, it wasn't completed then. It's now completed and it's working very well, and so that's very exciting. So here is where it is in the pantheon, if you like. Here's the Inouye Solar Telescope. Diameter is in feet and inches, 13 foot 11 inches, or 4.24 meters, and it's on Maui. And then here's Goody, the Goody Solar Telescope, 1.6 meters. The Swedish Solar Telescope. I didn't talk about the Dunn Solar Telescope. And then you see what we can put in space. Very much smaller, which is why we just don't get the same level of detail. Which is why we need to be on the ground to do this. So it's a wonderful telescope. It's complicated. You know, this has got very complicated optics, and it's quite hard to decipher. But let's just go through some of the basics first. 4.2 meter diameter. It's called an off-axis telescope, and we can kind of see why that is when we look at light path. And so here comes the light in from here, and it bounces off the mirror. But unlike most telescopes in the world, actually, most of the time when the light reflects off the mirror, it reflects back the way it came, or rather reflects up to a secondary here, which is on the same axis. So here the axis is the line which basically goes down the center of the mirror, is perpendicular to the mirror. And most mirrors, most telescopes, the light reflects back along that axis as well. But in this case, it's reflected off sideways, and that's so we have a completely clear aperture. The second mirror is not obstructing the first mirror, so it's not like a Cassegrain or a Newtonian or these most amateur telescopes are of that type. And then after what's called feed optics up here, which does rotation compensation and so on, the radiation is fed down this central hole and comes out in the instrument room, the instrument control, I beg your pardon, the Coody room. It's called the Coody Laboratory. And this is where the scientists hang out. And here you can see them all happily looking at the optics here. And so what we've got, the entrance aperture, the primary mirror. These texts is too small. I don't expect you to read it all, but it's just to give you an idea of kind of overall construction of this thing. And then here's the support building and so on. So it will be able to detect features 25 kilometers across at a distance of 150 million kilometers. Now, compared to what the James Webb Space Telescope is going to do with its much bigger mirror, it's not, you know, or the 30-meter telescope or whatever, you know, it's not a leader in any sense in terms of detail it can detect, but still we're talking about this is like a jumbo jet on the moon kind of angular resolution, so it's still pretty good. And the great thing about solar telescopes is the sun has got lots and lots of photons. The sun is very, very bright, and so you can take images very, very fast, and so you can see this amazingly dynamic activity. And so high detail and movies. You know, not much of astronomy has movies. We have movies, and we need movies because we see that, you know, the higher spatial detail we see, the more things are moving around. So we have to have movies. So construction started in 2012, funded by the US National Science Foundation to the tune of $344 million. So not cheap, but also not expensive in the grander scheme of astronomy. There were also contributions from Germany, from the UK, and from US universities. It saw its first light in December 2019, so the first clear path of photons right through the telescope, and should be starting science operations from the summer. Of course, everything's held up in the States and Hawaii by coronavirus, the same as everywhere else, but we are hopeful. We are hopeful. And I'm particularly hopeful because one of my students was successful in getting an observing proposal approved in a very competitive round. And so we're really looking forward to some data from the DKIST if there's a flare, if there's a solar flare. Let's just look a little bit at the Coody lab because, well, I want to actually emphasize a couple of things to you. The first is that there's a lot of instruments here. See, they're all named here. Here's VISP, visible spectropolarimeter. Here's cryo-NIRSP, cryogenic near-infrared spectropolarimeter. The visible tunable filter, the DL-NIRSP. Where's VBI? Here's VBI. This is this is a camera. This is something that makes just pictures. Everything else is basically some kind of spectrometer. Measures the spectra of the star and of the sun. And there's 5 instruments which are all taking light, incoming light from the telescope. But to get there, it has to be split up through lots and lots of mirrors. So it's a very complicated optical path. Necessary because, well, actually it's necessary because in the first place, the telescope had to have as small a footprint as possible on this sacred mountain. It couldn't expand over a large area. It had to be small. And so that means that the enclosure had to be small and the Coody table had to be small. So everything had to be crammed together, and so I had to have a lot of complicated optics to bend the light and feed it into different instruments. Now here is the deformable mirror, M10. Now this is M10. This is the 10th mirror in the system. Now every time you bounce light off the mirror, you lose a bit of the a few percent, not actually a few. In this case, probably the mirrors are 98% reflective. But you lose a couple of percent of the energy. And it's not like it adds. It's not like it goes 98, 96, 94, whatever. It multiplies. So you get 98% of 98% of 98%. So get your calculator out and do 98 to the power, or 0.98 to the power 10 and tell me how much light is left. You lose a lot of light doing this. So it's just as well the sun is bright. So this is the deformable mirror. This is where the adaptive optics happens here, and the others are called fold mirrors. So this rotating platform, it carries the 5 first light instruments, and despite the fact it weighs 150 tons, it can be positioned to an accuracy of less than the width of a human hair, so that the light goes exactly where you want it to and exactly tracks the movement of the sun across the sky and does the rotation compensation it needs to give you a good stable image. It's a very complicated thing, this. Okay, just a couple more pictures. Here's the, actually there's more to stilling the atmosphere than just adaptive optics. This is the actuators on the deformable mirror. There's about 4,000, is that right? I think I read 4,000. That doesn't look like 4,000, but I can't count. But these are all the little pistons that move the mirror up and down, thousands of times a second. This is the back of the main mirror, M1, and there's also pistons on the back of the main mirror. It's slowly pushed, much more slowly. I think it's only a few corrections per second, maybe even less, but it's slowly pushed to correct for things like the fact that the telescope is moving, so its shape slightly changes because of gravity, pulling on different bits, slightly different, exerting different stresses, thermal stresses and so on. So that has to be changed as well. So that's changing slowly to correct the image, whereas the adaptive optics is changing very quickly. So it's a complicated beast. I met the man when I was up there. I met the man who was responsible for the active optics, and he's a Scot. He actually came from Edinburgh. He used to work at the Astronomical Technology Centre, and now he's made this thing work. So that was its first light image. On the left-hand side here, it has only produced 2 first light images. I'd hoped when I agreed to give this talk, I thought, oh, there'll be lots of DKIST images by the time I give this talk, but no, there's still only 2. However, it's gorgeous. This is the actual Inouye Solar Telescope image. This is a simulation from what one of its competitors would see. This is the Dunn Solar Telescope. And, you know, it looks very nice with its resolution, but it's not a patch on what DKIST can do. We can see again here the convection cells, the granulation, which we saw before, and this filigree. And really, we start to see all kinds of complicated shapes in the filigree. Everything seems to be kind of knotted and tied and twisted, and it's very confusing. And one thing that we can be proud of, in fact, is that the UK built the camera. In fact, it built the cameras for all but one of the instruments. It was a company in Belfast called Andor Technology, which is now actually part of Oxford Instruments, I think. It was a spin out from Queen's University Belfast. In fact, they started off by building a very high frame rate CCD for another solar telescope. So, you know, what happened there was they had a science idea. In fact, it was on the Dunn telescope. They had a science idea that they realized they needed a CCD capable of taking many hundreds of exposures per second for, and a novel kind of CCD. So they worked in the university to develop that, and then realized that there was a commercial interest in this. And so a company was spun off, which went on to be successful, and then, you know, in a nice sort of circular pattern, was called back in to build the cameras for the DKIST. So, you know, good things can come from astronomy, from solar physics as well, in terms of the industrial applications. So, so there is quiet sun, and here is a sunspot at the native resolution of DKIST with adaptive optics applied. In fact, in this case as well, there's been some additional kind of processing done called the multi-object, multi-frame blind deconvolution. So there's another step of image processing done here, because in fact the DKIST doesn't have, it only has classical adaptive optics. It was too expensive to put multi-conjugate adaptive optics, but that will be the next upgrade. So it's brilliant. It's an immense success. So this was, oh, look at, sorry, I just spotted something. Look at this strange twisted thing up here. You wonder how the sun can make something like that, twisted so beautifully, like a little rope popping up through the surface of the sun. And this is the kind of thing you just couldn't see without this level of magnification. Okay, so what's it going to do? Well, again, it's going to look from the surface up through the chromosphere at different wavelengths, and eventually look at the corona as well. Now, this is an extreme ultraviolet image here, but in fact, DKIST can look at the corona too. And this is an image of the corona from an eclipse, which is just a beautiful image. And the observation was made in two different spectral lines. A red and a green line from the element iron, so that is almost more like actual colour. During an eclipse, you can see the whole corona, but DKIST at any one time will only be able to do a little box like that at very high magnification. So it would take a long time to build up a full picture of the corona, by which time it's probably changed and turned into something different, different shapes. But this DKIST is one of the instruments on it called in fact, there's two of them, but the cryo-NIRSP, basically, the cryogenic near-infrared spectropolarimeter, will be able to not just measure the intensity of the radiation, but to calculate, in some sense, measure the strength of the magnetic field in the corona, which has not really been done before. We can measure it on the surface of the sun. That's in fact what this map is showing us. It's the strength of the magnetic field and the direction of the magnetic field. And never really been done in the corona before, so DKIST will also be able to measure that. One of the reasons it can do that is because the sky brightness in Haleakala is very low. There's not much scattered light, and so you could put an occulting disk in front of the sun, and you don't get very much scattered photospheric light, and you can measure the corona very well. That's because it's just very, very clear sky, very little dust, very little moisture at these high altitudes. And so DKIST was sighted on Haleakala in Hawaii for that reason. So it's tremendously exciting, all of this. DKIST here is our ground-based microscope, but there's, you know, when I was putting together this talk, I thought, well, can I talk about our space-based microscopes as well? But no, there's just not enough time. But at the same time as DKIST going into a science operations phase very soon, we have these other two remarkable missions. Parker Solar Probe, which is going to very close to the sun within 0.04 astronomical units. So that's like 5% of the distance from the sun to the Earth, 4%. very close. It's got one imaging instrument on it. The rest are instruments which just measure the particles and the magnetic field in the environment of the spacecraft. So from some points of view, it's not so interesting for imaging, but it tells us about the magnetic field of the sun and the particles being spat off and all that kind of stuff. And then Solar Orbiter is going to fly into about 28% of the distance from the sun to the Earth. So it gets very close, and it gets a very high angular level of detail just by virtue of it being close to the sun, but still nothing like as good as what DKIST is going to do. But the three of these missions working together over the next decade or so, complemented by what we already have up there, like the Solar Dynamics Observatory, I'm sure are going to answer many, many questions about the sun, about its magnetic field, to some extent about how it affects us on Earth, and so on. So that's really all that I wanted to say. Thank you very much for your attention, and I'm really delighted to answer any questions that people might have.
Thank you so very much, Lyndsay. I know you said that I didn't want to be disappointed, and I can tell you I certainly wasn't. I certainly wasn't disappointed at all. I got one point, I got so engrossed I forgot I was running the Zoom meeting. Yeah, as I said, there's quite a few questions come in, so I'm going to hand over to Rich Oakley, and he's going to ask those questions to you.
Okay, yeah, well, that was a great talk, Lyndsay. Very, very impressive. So thank you very much for that. Lots of questions in. We've had a couple of questions based on the same theme, really, and bearing in mind how I used to set fire to grass with a magnifying glass when I was a kid, and I was aware even then of the intense heat. How do they dissipate the heat that gets into this instrument? And that's
a very good question. I don't know if anyone noticed on the slide showing this. I could share it again if we want to.
Yeah, go ahead. Yeah,
do that. Just share that. Hang on, I need to mess about with my.
It's pointless having good slides and not using them. So
yeah. Okay. So let's see.
You'll, I think, come in at your last slide. Oh, right, yeah.
Right, okay, so so here, you might be able to see it says heat stop, and it's up there. This is exactly the thing that you're asking about.
Yeah.
So liquid cooled metal donuts is what they call it. So there's a ring around close to M2, the second mirror, and that just basically cools the second mirror. It conducts the heat away from the second mirror, the secondary mirror, eliminates more than 95% of the heat from the system. I expect that some of the other mirrors have got their own cooling as well, but this is where the main job is done. I mean, the telescope as a whole actually has to be cooled. Everything has to be kept cold to reduce the dome seeing, and the way that they do this is actually with ice. They make ice overnight. They make ice and store it. When I say they, I mean it's not a lot of guys with shovels. You know, it's an automated ice, big refrigerators making ice and storing it in a remote room. You know, somewhere out the back here. It stores the ice, and then during the day it's fed through pipes into a cooling system inside the telescope. So it's actually quite ecological in that sense as well. They do it when electricity is cheap, and it can be, you know, it can be done efficiently. So that's how they cool it.
Right, I was just thinking as well, it's a light colour, which I presume helps a bit as well, that the whole telescope's quite a reflective colour as well, which sort of helps a bit, doesn't it?
Yes, the whole of the outside is reflective, and also the apron around here as well is white. Deliberately it's painted white, again to reflect the radiation.
Yeah, I guess it must have upset the natives a bit, because it actually makes it a lot more visible, because if you could just, you know, paint it the same colour as volcanic rock, you could sort of at least hide it a bit, but it does make it stick out a bit, doesn't it?
You can see it from the ground. It's visible from the ground. But you know, one of the annoying things is that it's on that site up there on Haleakala. There's also the US Air Force radar tracking station, which looks like just two great big silver spaceships. and it glints. You know, that actually glints. It's reflective. It's horrible, and that's, you know, that's the thing which and that was built with no asking at all. It was just like the US Air Force, plonk, you know, down it goes. And so that's really the offensive thing up there. It's been up there for a decade or so. About DKIST, or more than a decade, I think. But DKIST, you know, was next in the firing line, put it that way. But I think there probably have been great wrongs done to the Native Hawaiian community in that respect. So they've worked very hard actually on the DKIST site to keep the Native Hawaiian community involved. They have a representative from the community who checks that everything is being done correctly, because, you know, you're not allowed to take this. The mountains are where gods live, or maybe they are gods, I'm not quite sure of the details, and you're not allowed to take anything off the mountain. So you're not allowed to take stones, and that was another problem. So when they were digging out to make the foundations, they couldn't move the rubble off the mountain. The rubble had to be just put somewhere else and appropriately blessed and so on. And even like the trucks had to be washed down so that dust didn't get taken off the mountain. It all had to stay there. And so it was done with great cultural sensitivity and great involvement of the Native Hawaiian community as well, but still not without trouble.
Yeah, well done to them for actually, you know, attempting to do this, because it is good. But it also represents a big investment in Hawaii as well, doesn't it? You know, so, you know, they've got to, you know, there's pros and cons for everything, isn't there? So it's good that they're, you know, taking it into account, but also there are benefits as well, you know.
Mm-hmm. Indeed.
Now, a question here from Angela Nicholson saying, angular resolution question.
Mm-hmm.
What is the 1.22 constant?
Yeah, good question. How much maths do you know?
Well,
that's a very good question. So how can I? It comes from the physics of a process called diffraction. And diffraction is what happens to light when it goes around an edge. And the edge in this case is like the edge of the aperture that the mirror is in, the whole edge of the hole, if you like. And it's a bit complicated, but you get both diffraction, which is the bending of light round an edge, and also interference. And that gives you, now if I had my first year astronomy notes, I could show you, but I haven't got them here. But it's a combination of these optical effects. Now this is not, there's two kinds of optics that we think about. One is geometric optics, which is where you just think about rays of light bouncing off mirrors and so on. And we just think about reflection really in that. But the other is physical optics, where we think about diffraction and interference and refraction and what happens when photons pass through media and scatter off edges and so on. And the 1.22 comes out of diffraction from a circular aperture, from a circular hole or around a circular edge. If it wasn't circular, if it was like it had a slit, that 1.22 would not be there. It is not there because the mathematics is slightly different. This calls on something called Legendre polynomials. No, it's not Legendre polynomials. I forget. Bessel functions or something. Yeah, Bessel functions, that's what it is, it's Bessel functions. So it's a fairly arcane piece of mathematics. To all intents and purposes, it's just alpha is lambda over d, and that's easy to remember. The 0.22, we don't care about that very much.
No, it's obviously a correction that you have to put in.
You do have to make it, yeah. If you want to squeeze every last drop of angular resolution out of your telescope, you're going to have to think about that 1.22 rather than 1.
Fair enough, yeah. It's a good question here from Eric Walker of Highland Astronomy Society. Can the multi-adaptive optics be retrospectively fitted to any other research scope, is basically what he's saying.
Yes, it definitely can. So it's let me see, it's on the Big Bear Solar Telescope, or the Goody Solar Telescope at Big Bear Lake. don't think that it's on the Swedish Solar Telescope yet, but it certainly can. But it needs space on an optical bench to do it, because, you know, if we remember looking at this picture here of the Coudé room, this is basically, there's an equivalent to this in every solar telescope, a place where the light comes in and is split off into different instruments, and before that happens it has to go through the adaptive optics. Now if you have not one mirror but 3 mirrors, you've got to find space for them in here or in the equivalent, and that's not always easy, but in principle, yes, you can retrofit adaptive optics.
Right, okay, that's great. It's right, let's have a look. I've got a question here actually. What are the current big areas of research? You mentioned the specular as being a big area of current activity. Is there anything else that's you know, getting a lot of people interested? Or
yeah, well, before we just after first light, we released a paper called the Critical Science Plan of the DKIST telescope. The critical science plan is the science it's supposed to do the first couple of years, and that's a paper which is 40, 50 pages long, something like that, describing everything that we thought we could think of at that time, but now more ideas have come along. But things like the formation of sunspots. How exactly do sunspots form? You know, when a sunspot is a magnetic thing, a bit of the sun's interior magnetic field somehow pops up through the photosphere and, you know, forms this kind of dark feature in the middle, but we really don't know how it happens because, as I said, they don't pop up fully formed. You get lots of little things like this, or maybe like this dark thing, and they kind of all group together. Now, why is that? Why do they all group together? Is it because there's something that's happening under the surface, or are flows on the surface pushing them together? Why does the penumbra of the sunspot form? The umbra of the sunspot, the darkest part, is where we think the field is basically coming straight up, straight vertical, perpendicular to the solar surface. But here, the magnetic field is curved over, and we're not quite sure why that happens either. You know, almost anything, the exact physics of convection, why we get convection cells, we kind of understand. There are very good numerical simulations of this. You can make something in a computer that looks very much like convection, but only if you twiddle particular numbers inside the calculations. If you tune them. So we'd like to really understand what those important numbers are and how they affect convection. Flares. Where are the flares? Where were the flares? Where's the flares? Oops, where is it? Yeah, flares. So what does this vast onslaught of energy in a solar flare do to the lower atmosphere when it hits the lower atmosphere? And can we, in fact, this is something that I'm very interested in myself right now with my students, is can we use this radiation, not just the images that we see out here, but also the spectroscopic information, which I haven't talked about here. How can we use that to work out what's actually happening in that heated atmosphere, where the energy is going, how it's changing the atmosphere? And ultimately, we hope we can learn something about where the energy came from and how it got down to the lower atmosphere in the first place. So I could say a lot more, but that just gives you a flavour. There's a huge variety of questions about the photosphere, about the chromosphere, about flares, about sunspots, about some people get really, really excited about tiny little things, you know, tiny little bright blobs that come and go. There's these things in the atmosphere called Ellerman bombs, which are very, very bright energy release, tiny bright energy releases in the photosphere, and nobody knows quite where they come from either. So, you know, and as in any discipline, you can get obsessed about the tiniest things, and people do get obsessed about the tiniest things. You hope to learn something about the bigger picture by studying the tiniest things, but these let's see, I don't know whether there's a picture of an Ellerman bomb here. Probably not, but let's just have a look. No, I don't see one here. But if you might, but element, well, maybe that's one here. This very tiny bright thing right here. It just looks insignificant, but it flashes on and off. And where does it come from, and what's it doing? So people can get obsessed with detail, but the detail does tell you something about the bigger picture, because those element bombs, these tiny bright things, are probably there because of, again, because of magnetic fields, and they're scattered throughout this whole area. And so it tells you that there's strong magnetic fields permeating this whole region. So how does that happen? Where does that come from? How do the fields organize themselves, etc., etc.?
Right. Yeah. Okay. Well, yes, it's like anything, any field of research. The more things you answer, the more questions you have, isn't it?
Yeah.
Question. Again, another excellent question, and that is, what distance do the pistons deform the adaptive or the adaptive mirror by?
Oh my goodness, that's a very good question. I don't actually know, but I could.
Well, I tell you what, we've got a few questions we won't get to. So what I'll do, Lyndsay, is we'll email these to you.
Yeah, and I'll try and answer them, because that's a very good question. I'm not sure. I'm sure it's in the order of nanometers, comparable to the size of the wavelength that you're trying to correct. So that would be my first guess. So very tiny corrections, yes.
Yeah, well, that's a pretty good start, I would say. Yeah, it's
you could always pick them up in the in the chat in the gathering afterwards if you wanted to.
And go, that's right. Yeah,
go from there.
Okay.
So.
Right. Well, thanks very much, Lyndsay. Anyway, and we'll pass over to Pete now.
It's you first, Rich.
Oh yes, better say the vote of thanks. Yes, yeah. Well, Lyndsay, thank you very much for a really, really interesting talk. The great images, great animations, and a lot of information, and a very informative presentation. Now, we've got a glass here for you that will, if I can just get that in the mirror, in the camera lens, that we'll be sending to you as a means of a thank you for a very, very excellent presentation. So thank you very much. And
I can add that to the set. I think we've got 5 now, maybe. Yeah. So
they said that if you get 6, you can trade them in for the decanter, but they've got to be a matching set, and we've been changing them every 2 years, so hard luck.
That sounds like something that there's no hope in winning unless you ask it every 3 months.
Yes, it's a bit sneaky, that.
But we might want. Well, we might have to see when you come out next time. We'll see if we can get something in one of them glasses for you, because as I say, we should. It is such a shame that we couldn't get you to come up here tonight and do this in person, but we will get back to that one day. I'm sure we will. And if you do, can you bring the sun with us? Because you've been hailing here tonight. So.
Not good.
Right, so Lyndsay, thank you so very, very much. It really was good. And as I say, you can always tell by the number of questions we have coming through. But what we're going to do now is we'll go for the break. We'll have a quick 10-minute break, so back at 9 o'clock. Rich will be coming back in with the members' photos. As I say, Stuart will have the space news, and then we will go to my bit of club news, and then over to the chat for a wee drink and a blather together. Okay. Once again, Lyndsay, thank you so very, very much. And we'll see you later.
In the chat and the next session.
I'll send you the link for the gathering in a minute as well through an email. Okay. Okay, everyone, we'll go to the break. And welcome back, everybody. As I say, that was a fantastic first half. I think you will agree. Lyndsay's talks always seem to go that way. She's got such an enthusiasm for her subjects, as you can tell. She did ask, earlier when we'd done the practice session of how many people we normally get on these meetings. I can let you know we've had over 40 people tonight, which is pretty good, pretty standard, but it's really good that you all come along and join us. It's hard to say just how many, because you do get some couples, but there's over 40 people, I'm going to say. But anyway, we're going to carry on now. If Richard, if you're ready, we'll go to the members' photos.
Yeah, that's superb. Thanks very much, Pete. Yeah, we've got a few photographs in, and they're largely of some pretty spectacular aurora images taken. The first couple are from Sigma member Mick O'Donnell, taken from the West Beach at Lossiemouth, and they show the sort of different sort of greens and colours of the aurora with the curtains and everything. Very spectacular images with the towers and everything. So great image there from Mick, and thanks very much, Mick, for that. And I'm always impressed by what the camera shows that you can't actually see these things when you see them with the naked eye. But no, great pictures there, Mick. And I think there's two there. We've got another one, haven't we? Yeah, this is again another spectacular image, and quite a bit of night sky going on behind it. Mick's managed to pick up as well there. So I think we've got some photographs coming up from Alan Tuff, and that will show us some more deep sky or deep space objects as well. But this is again taken at Hopeman Beach in Murray, with the slight relaxation of the lockdown. Alan's been able to get out and about and take some more images. So this one's a great image, and again with the purples and greens and the curtains and towers on display again. It's and then if we move to the next image, we've got a few deep sky objects here that we'd like to draw your attention to. So if you watch the laser pointer, first of all, we've got the Andromeda Galaxy, and quite deep in the sky here, and only basically visible above the sort of the greens and on the green sort of purple boundary of the aurora. So and then if we move up a little, we've got Cassiopeia and that bright star there. And then if we move west from that, we've got the double clusters in the Perseus constellation. So some pretty interesting deep sky objects there, and at a time of year, I mean, this was taken the 17th, 18th of April, so and quite late on, 11:15 at night, but it's quite an achievement to record these deep sky objects at this point in the year. And then there's a passing meteor there as well that has just streaked through the shot. So well done, Alan, and thank you very much, Mick, for those great images. And that's it for those. Thank you.
Okay, thanks very much, Rich. Okay, so moving on now. Let's say for some fantastic images there. Well done, both of you. It says moving on. There we go. We will move on to Stuart, if you're ready for your space news. I'm hoping you're ready, Stuart.
Yeah, I'm here.
I'm glad to hear that.
Okay, good evening, everyone, and welcome to Space News.
Yeah, we got that over to
you. Got that? Okay. Right, what I've selected is a few updates from last month's talk and some other items that have occurred during the month. It's interesting, a lot of media attention is now given to space activities, so you may well have seen some in the newspapers or on the news some of the events. On the information I've got on tonight may have been overtaken by later activity. So if you see anything, perhaps you'll let me know afterwards if there's any new information. Okay, so we've got SpaceX Starship SN11, Blue Origin rehearsal for the New Shepard, the latest Hubble image, new conjunction agreement with NASA for SpaceX, astroscale demonstration, Ingenuity update, demonstration rocket for agile cislunar operations, and SpaceX launches 4 astronauts. As you remember, the SSN-11 on the 30th of March reached a maximum height of 6.2 miles. Its ascent phase, transition to the horizontal and control during free fall were all good according to Elon Musk. However, there was a small methane, CH4 methane leak, which led to a fire on engine 2, and this fried some of the electronics, and it caused a hard start during attempting to land a landing burn in the methane turbo pump, with the result that it blew to pieces. And this is the only shot I've can find where it actually shows anything happening to that actual explosion. And there's 2 parts falling down. Not to be outdone, SpaceX put SN50 on the launch pad, ready to launch on the 8th of April. Now it's SN15 because 12, 13 and 14, which had been started to be built, were overtaken by design developments following the earlier flight trials. So SN15 was the latest version. It was on and off from the April the 8th to launch. It was ready to launch. Apparently they closed the road quite a few times, which passes the launch site. And I was expecting that to be the last picture I was going to give you. However, yesterday, and what I'm going to do is I'll fast forward this because it takes a little while, but I'll show you the launch and the recovery. This is the countdown. As you get in airborne, it then disappears and flies for a little while. And if I move it along to six minutes, a little bit of break up. It is just to prove that it actually did a landing. I'll let the smoke clear just to prove that it did land. Okay, so that was SN15, a success, and Elon Musk must have been very pleased with that. However, he was probably upset by the fact that earlier, if I go back one, Jeff Bezos' Blue Origin's New Shepard rocket launched on the 14th of April. And this is his reusable suborbital vehicle. And it went through a test run, not with astronauts, but with company personnel to go into the capsule prior to launch, do all the procedures for setting up, then came out before the rocket was launched. So I'll show you a run of this, and I'll do the same again. I'll fast forward. These are the two personnel going in. Go through the check procedures, they then come out. Obviously not astronauts, but this one's quite impressive. The 1.56, it then inverts, and this is it coming down. That's it landed. As well as the rocket landing, it was also the capsule came down successfully as well. You just see it touch down. Again, the company personnel went inside and went through the leaving checks as well. Now I'll just go back to that one. The launch for passenger flight is the 21st of July. And the auction has just opened for anyone who's interested in getting a seat on board. I should imagine the only people likely to be able to afford it will be Elon Musk or Jeff Bezos. But anyone interested in the audience is quite welcome to apply. Okay, so that's New Shepard. This one was an update on Hubble. Remember Hubble last year had a problem and they updated the software. Well, they've managed to come up with some rather spectacular views of Vale Nebula in the finest detail ever, so they say. It's using the Hubble's Wide Field Camera 3, using 5 different filters. New post-processing methods were used to further enhance emissions from doubly ionized oxygen, seen in the image in blue, and ionized hydrogen and ionized nitrogen, seen in red. Now, I'm not an expert in that area, but perhaps Lyndsay knows more about that aspect of it. It's the second time Hubble's produced those images, and it was 2017 where they produced a previous one. Oops. Sorry, that's the first one, and that's the 2017 image. Next one is NASA and SpaceX have now had a conjunction assessment. NASA was concerned that the amount of traffic coming from the satellites that SpaceX is launching and the possibility of a collision, they wanted to have some agreement between SpaceX. So they've drawn up a conjunction assessment, which is specific to SpaceX. The one they had previously was a general one. And this was done on the 18th of March. The concern was that they didn't know when some of SpaceX's launches were going up, and they wanted to protect their assets. And if I produce that, this is what they produce as an illustration of the assets that they have in space, and they wanted to make sure there was no collision. So the agreement is that they will provide SpaceX with details of their assets, and SpaceX will provide them of the details of what they're launching. There'll also be some consideration regarding the illumination of SpaceX's satellites in terms of Starlink ones. And the agreement as written is also transferable to any other company that they feel they need to do the same with as the traffic increases. And when you think of 12,000 Starlink satellites eventually being put up in space, it must be quite dangerous. And it was interesting that just after that, that the call it the get the name of it, OneWeb reported that there was a near miss of 58 meters between one of Starlink and their own OneWeb satellites. Now, Starlink is at a lower orbit than OneWeb, and OneWeb passes through it, and it missed by 58 meters. I looked at that first and I thought, it must be 58 miles, but 58 meters is quite close for a miss. When they reported it, everyone was in a state of panic, but SpaceX then said later on in the end of April that it wasn't such a disaster after all, but OneWeb has not actually rejected that. They've not come back and said, no, it was a near miss. So you can understand the concern of NASA in terms of wanting to avoid any collision. And I'm sure OneWeb will be another one that they want to actually do and set up an agreement with. SpaceX still launched 60 more satellites on the 7th of April, which went fairly well. And it landed 9 minutes later on the recovery vessel safely. And it was the 7th landing of that particular rocket. And the success actually shows how well SpaceX is doing in certain areas. But also what was reported was last week was the Chinese have launched another section of their space station, the Heavenly Harmony, and the Long March 5B rocket, after it delivered it, was left out of control in low orbit with no one knowing exactly when it's going to come down. And I thought that was quite a dangerous situation to be in. And I think this is the second time that the Chinese have done that. However, a new method of capturing space vehicles or space capsules has been put up by Astroscale. And its intention is to clear space junk. And what he's done is set up a test. It's a Japanese-based company, and it launched on the 22nd of March and was among 38 payloads that were carried by a Soyuz rocket. Its first all-commercial rideshare mission for the Russian company GK Launch Services. You'll test a magnetic docking technique to remove space debris from orbit, and it will consist of satellites stacked together, two satellites stacked together, a 385-pound servicer and a 37-pound client. And the service satellite will use GPS to locate space debris and then latch onto it with a magnetic docking plate to carry it down toward Earth's atmosphere where it will burn up. and that's the vehicle. The square box at the end is the client, which is the test client, and its intention is to have three aspects of the test. One is to release the client, which it will then immediately pick up again, just to show that there is a possible pickup. The next, it will release it and it will catch it doing 18,000 miles per hour, and again catch it and lock it onto itself. And the third one will be where it will release it and treat it as a proper search using the GPS, find it, locate it, catch it, and then come down to Earth where it will burn up. Its intention is that the block that it catches will be fitted to future launched satellites, so that when they come to the end of their performance or they need to be brought down, it will be able to lock onto the satellite via that magnetic block and bring it down to Earth more quickly. The Astracal is also looking at the protocol for future activity of reducing space debris. In April, which was on the news, Ingenuity test flights took place, but it started off with a little bit of a problem. Here it's on the 7th of April, it set out, it had a few issues with going from pre-flight to flight, and they had to do a minor modification and reinstall the software before they could go and do their planned testing. And it achieved all its main technology demonstrating goals on 3 flights, which occurred on 19th of April, April 22nd, and the 25th of April. And on the 30th, it lifted off on its 4th flight and covered 872 feet and reached a top speed of 8 miles per hour during a 117-second flight, national officials stated. And it will now embark on a new operation demonstration phase, exploring how aerial scouting and other functions could benefit future exploration of Mars and other worlds. Again, in April, there was a demonstration rocket for agile cislunar operations. The Defence Advanced Research Projects Agency, DARPA, has selected 3 big space companies for the first phase of a large project to test nuclear propulsion above low Earth orbit by 2025. General Atomics, Blue Origin, and Lockheed Martin each received contracts for the demonstration rocket for agile cislunar operations for the first phase, and the teams were selected due to their ability to develop and deploy advanced systems, reactors, propulsion, and spacecraft. What they're after is a more maneuverable vehicle for military activity, which is interesting to think that we're going into into military activity in space. And that's the vehicle we're looking at. So at 2025, that should be on its way. And the idea is that it will, NASA is also interested because it will reduce the time to Mars by a half, and it will also improve the maneuverability because of the electrical controlled power is very slow, and the chemical controlled power is also very slow. So it'll be able to be very, agile in space. And on the 23rd of April, a space SpaceX Falcon 9 rocket carrying 4 Crew 2 astronauts lifted off from the Kennedy Space Station and headed for the International Space Station. That's it arriving at the space station, and 11 astronauts. It must be a bit tight, I should imagine, on board with all those around, because there was the original Crew 1 who went up in November, Crew 2, and the staff that's remaining on board. And they came back. It was the first night recovery. Dragon Resilience, as it's called, and it landed in the Gulf of Mexico on the 2nd of May. So that is another success for SpaceX, and that's his 3rd launch of astronauts, taking into account the first one, which was a test launch. And that's it. Thank you.
Thank you very much, Stuart. We had one question come in while you're saying that, and that was from Eric Walker saying, how many times can the first stage of Falcon X be used? I don't know. Go on, do you know?
I don't think they've actually given a number of times. I think it's on check-in afterwards on its.
Yeah, because I've done a Google search and there don't seem to be any sort of limit.
I think it's just basically that when it comes back, they assess it. They don't like them landing in the sea because of the impact of corrosion after a while. So if it goes in the sea, that normally writes it off.
Yeah, gotcha.
But if it does a dry landing, it's really like an aircraft. If it does a dry landing, it's
I can use it again
on condition. Yeah, just check it and fire it up.
Right, thanks for that. You beat Google. Well done.
Okay.
If you want to just end your share there, then please. Okay, everyone. We just finished off with a little bit of the sort of club news. AGM, obviously that's coming up next month. You should have all received your the minutes, the voting forms, and the agenda. If you haven't, let me know and I'll get it sent out to you. I believe there's some sort of vote went on yesterday is being counted today. I'm not sure what it's about, but the important one is on June the 4th when we got our AGM. Okay. If you sorry, Stuart, do you want to just kill your mic and your camera, please?
Oh, sorry.
Yep. As I say, the voting forms need to be sent back to Richard either by email, or posted to him. All the information is in the newsletter, but that needs to be done by the 24th of May to give us time to actually get everything organized ready for the AGM on the 4th. Okay. Sigma on YouTube, as you know, all our meetings now go up on our YouTube channel as unlisted to start with, so it's just a benefit for members. And then in about 6 months' time, we normally put them up, if we're allowed to by the speaker, put them up live to anyone who wants to come and look at them. Okay. Yeah, I did mention there was a typo in the, going back to the AGM minutes, there was a typo in the address for Richard. It's not minefield, it's Milnefield. Okay, mind you, I think some parts of Elgin could probably do with a minefield, but that's just me. The BAA summer meeting, you remember we were meant to be having a BAA summer meeting last year, and that was postponed to this year. Well, it's always been postponed again until next year, but they are going to be doing an online meeting on Saturday the 26th of June. There's two talks arranged, one for 11 o'clock and one for 2 o'clock, I think it is, but more information on that will go out to everybody in the Sigma newsletter for next month, and I'll pass it all on to the other associate club members that you know we've got here. So be free to anybody anyway, so anyone who wants to come along can come along to that. That's Saturday the 26th of June, so it's a date to put in your diary. And maybe we'll get the live one next year, maybe, hopefully. Let's just keep our fingers crossed. The Sigma telescopes, I know I said you could borrow them, you could if you want to use them, but see the way we are in Murray at the minute with the increasing numbers, I don't think we better go handling stuff around and meeting up too much. So therefore, that's on hold again for now. Don't forget to invite a friend. I believe we had a new visitor tonight. you're very welcome. Hope you enjoyed the meeting. Always like a little bit of feedback, and I think it was Mick that invited you. So please do give us a bit of feedback. And if you're thinking of joining, just let Mick know, and he can send you out the membership forms. But say if you've got anyone you know who's interested in astronomy, who's never been in an astronomy club before, just let them know about us. Give them the link, give them my email, and we'll get them sorted and get them in the club. As I say, the meeting, the Zoom meeting gathering is going to be straight after this. I see that Richard's just put the link straight into the chat there now as I'm talking. All you got to do is just click that link when we finish here. You should take you straight over to a waiting room. It doesn't normally ask you for the password, but if it does, please copy the password down now. It's in the chat, and password and the meeting room number. It doesn't normally ask for that, but sometimes it might do, and it won't let you in otherwise. Failing that, the information for that is in the newsletter as well, and also in the email that the newsletter came with. Don't forget, if you've got anything for me, any sort of thoughts, ideas, let me know. Just send me an email. As I said, the next meeting is June the 4th. Just letting us the day before my birthday, if anyone's interested in that, It's the AGM, plus then we'll have a talk by Matt Wittmar from the Royal Observatory in Edinburgh. Once again, another intriguing title to a talk: Satellite Data and Transplanetary Ecology, How Space is Changing Our Worldview. Sounds very interesting again. Very, very interesting. Okay. Yeah, 21 again. Yeah, whoever put that up. Yeah. For the third time at least, I think, noon early. No, second and a bit. Sorry, it's just a chat come up there asking if I was 21 again next month. So with that, I want to thank Lyndsay for her wonderful, wonderful talk. As I say, you always tell a good talk by the number of questions, and we didn't have time for them all, but hopefully you can ask her a few more in a minute in the next meeting. She said she's coming over along with her husband, Hugh. Remember, Hugh gave us a talk on astronomical dimming a few months ago. Rich, thank you very much for doing the Q&A and the vote of thanks and everything else. There, you're done. Mick, for being in the background as a co-host. Stuart, Space News, fantastic once again. And most importantly, thank you all yourself for coming along from all over Scotland, well, and even the UK now. So we've got members who are joining from down south. And with that, we'll see you in a few minutes. We'll have a little drink together, hopefully, and an evening's talk and a bit of fun. So stay safe, and more importantly, stay well, and keep looking up, and we'll see you in a minute. Good night, everybody.